that we need to have XL and XU, which is interval that bracket the root. And the idea of the open method is only one initial guess, which is not necessarily bracket the root. Means that here we have one initial guess that we denote as X0, and this one is not necessarily bracket the root, means that it is not interval. This initial guess is already the estimated root. Okay, but initial estimated root. Normally, the chosen values must be close to the actual root that can be found by plotting the given function against its independent variable. Means that if you use graphical method, you can see the idea, you can see actually where the graph cross X exists, and you can choose initial value based on that point. In every step of root improvement, XR of previous step is considered as the previous value of the present step. Okay, means that XR of the previous step, let's say we start with the iteration I equal to 0, we'll got here X1 as our XR. Here we denote as this one is actual estimated XR. And then when you want to go to the next step, I equal to 1, you'll got X2. But to compute this X2, you need this X1. Means that X1 from previous step is considered the previous value of the present step. We will see later the formula. In general, open method provides no guarantee. So this is the disadvantage of the open method, that is, it is not guaranteed that it will converge, but in bracketing it's guaranteed it will converge. But class, once it's converged, it will converge faster than bracketed methods. Here we have two types of method. The first one is Newton-Raphson and the second one is Secant method. We'll go first to the Newton-Raphson method. So class, this is the idea of Newton-Raphson method. It is open method for finding roots of fx by using the successive slope of the tangent line. Means that here, if we have this graph, for example, and the root is this is our initial value. The initial value is here. Okay, from here you can get this one its function. You can plot a tangent line. Okay, you can plot a tangent line here. From this tangent line, you will go to this x1. So this x1 is actually the next root that we calculate. And based on this one, okay, we have this one as our function of x1. And then from here, we draw a tangent line. Then it will go to this x2. And then from x2, next, we have here a function of this x2. And when we draw a tangent line, finally, it will go to this true solution. And this is how Newton-Raphson method works. And if you see here, we use a tangent line. If you use a tangent line, so it has a relation with the derivative of the function. So class, how can we estimate the root using this concept? We need to use here a slope, because slope will give us means that slope of the tangent line. Because we have a tangent line, we will compute the slope. For the first iteration, we can compute a slope using f prime x0 equal to f x0 minus 0 divided by x0 minus x1. So if based on this, actually our root that we want to compute is x1. Okay, so we can rearrange this function such that x1 becomes subject. This x1 we need to move to this side. F prime x0 we need to move to this side. We rearrange this one. We'll got x1 equal to x0 minus f x0 divided by f prime x0. But class, when you estimate the root, you will have many iterations. We cannot just write it as 1 and 0 here. So we use notation I, means that I refer to the iteration. For the iteration, we will have the formula here become I plus 1, xi plus 1, okay? Here is 1, so here x0, so xi plus 1 here, equal to xi minus function of fxi divided by f prime xi. So this one is the formula for Newton-Raphson method that you will use in the finding of roots using this method. If you see in this formula, we have a derivative of the function. So class, for this method, you need to know how to find the or how to differentiate function. We go to the algorithm of Newton-Raphson method. We have here step number 1, we need to choose initial value and find its f prime x naught. And then step number 2, you need to compute the next estimate xi plus 1 by using Newton-Raphson method. So Newton-Raphson formula, this is Newton-Raphson formula. And then we calculate the approximate error epsilon A. We compare if epsilon A less than epsilon S, we can stop our iteration. Otherwise, we will repeat, go to step number 2. So class will solve the problem using this algorithm. We'll go to the example. So this example asks us to find or determine the first root of this function by using Newton-Raphson method. And you need to use the initial guesses of x naught equal to 0.3. And then the question asks you to perform the computation up to 3 iterations. Here, because our function in terms of sine x, remember class, when our function involves trigonometry, you have to change your calculator to radian mode. What we need to do here, we have this one is our function. And if you see, based on this question, we have our x naught equal to 0.3. Okay, and then in computing using Newton-Raphson method, we need to use a formula xi plus 1 equal to xi minus function of xi divided by f prime xi. In this case, class, you see we have a derivative of the function. So our first step here, we need to find a derivative of our function. Here, we have a exponential of negative x sine x minus 1. So how can you find derivative of this function, or how can you differentiate this function? This function actually involves the multiplication of exponential and sine function, which is minus constant. You differentiate constant, understood, it will be equal to 0. But you differentiate this part, you need to use product rule. And how to do that? We let here, okay, let u equal to a exponential negative x, and then v equal to sine x. And then class, we need to find u prime. U prime, if we have this function as u, means that equal to negative a exponential negative x. And then v prime equal to cos x. The product rule, the derivative of the function equal to the formula of u v prime plus v u prime, means that equal to u a exponential negative x, v prime is given by, here is v prime is cos x, and then plus v is given by sine x, so plus sine x, but times here u prime negative a exponential negative x. So class, when we rearrange this one, we'll got a exponential negative x cos x minus a exponential negative x sine x. And then when we factorize this a exponential negative x, we'll got this one as our solution. But class, you differentiate this part, actually it is minus 0, so we don't have to write this 0. For the first iteration, we need to use this formula. Okay, in this case, first iteration actually class, our I equal to 0. When I equal to 0, we substitute I in this formula, we will have x1 equal to x naught minus fx naught divided by f prime x naught. So we have this formula. But class, x naught is given in the question, it is equal to 0.3 minus fx naught is a function of x naught, that is function of 0.3. Means that you have to compute here function of 0.3 by substituting 0.3 in original equation from question. So it is a exponential negative 0.3 sine 0.3 minus 1. You will got this one as your answer. remember, change your calculator to radian mode. And then our f prime 0.3 here equal to, we'll use this function. So if you got wrong here, you will got wrong at this point, and then you will got wrong for all iteration. So class, we have a exponential of negative 0.3 plus 0.3 minus sign. This exchange to 0.3. Use your calculator, you will got 3.9104. So this is fx naught, this is f prime x naught. We substitute 0.7514 for this fx naught and 3.9104 for this f prime x naught. You'll got this one as the formula. You use your calculator, you'll got 0.1078 as the solution. Class, for bracketing method, first iteration, we unable to compute epsilon A because we don't have previous value. But for open method, the first iteration you able to compute epsilon A because this x naught is not interval. This x naught is actually the initial estimated root. In this case, how to compute epsilon A? Equal to absolute value of current solution, that is 0.1078 minus previous solution, that is from initial value 0.3 divided by current solution times 100%, you will got a very big error, that is 178.18%. So the question asks you to do up to 3 iterations. It is not yet finished. We need to go to the next iteration. And actually for this one, you can use table. Okay, I will show you how to use table. Previous computation, we have from question x naught equal to 0.3, we have x1 equal to 1.078. So now I want to show you how can you use table to solve by using Raphson method. Let's say we draw this table, and in our table we have here, for the first column it is I, okay, this is I, and then we have xi, function of xi, and then we have function of derivative function of xi, and from here you can compute your xi plus 1, and then it is epsilon a. So class, based on this, we have it from for first iteration. Okay. For I here, first iteration, we need to put also here number of iteration. Okay, this is number of iteration, which is for the first iteration, our I equal to 0. When I equal to 0, xi, which is x naught from initial value is 0.3. And then we compute function of 0.3, we got 0.7514. And then we compute function which is derivative of function for 0.3, which is 3.9104. And then we compute xi plus 1, that is x1, we got 0.1078. Sorry class, here 0.1078. And then previously we did for epsilon A, we got 178.18%. And then based on this, we need to increase our iteration because this one is just first iteration. And question asks you to do up to 3 iterations. For iteration number 2, whereas here our I now we need to increase as well. Instead of 0 become 1. And then when I is 1, so we have x1 equal to 0.1078. So this is x1. You need to change, you need to choose this one as your x1. That is, previous answer will be current initial value. So here 0.1078 as this x1, and then we need to compute function of 0.1078 and also f prime 0.1078. How to compute this? for the first function here, its function we use from question, which is a exponential negative x. So exponential negative 0.1078 sine in bracket positive 0.1078, which is minus 1. When we compute this one using calculator, we'll got the answer here, negative 0.2270. And we did for its prime here, which is derivative of that function, we have a exponential negative 0.1078 times cos 0.1078 minus sine 0.1078. You use your calculator, you will got this one. The answer is 6.3674. And then we can compute this xi plus 1. Remember, I is 1, so xi plus 1 become x2 equal to x1 minus f x1 divided by f prime x1 means that minus here, okay, minus x1 divided by f prime x1. We have here 0.1078 minus this one, okay, negative 0.2270 divided by 6 point, which is f prime x1 3674. When we compute this one, we'll got here the answer 0.1535, and then you can compute epsilon a, you will got 24.84. How to compute this epsilon a? This solution, okay, minus this one divided by current solution times 100%. Then class we do for third iteration, which is here I equal to 2. And then for this one, the previous solution here will be initial value for the next iteration, that is 0.1435 here. You compute its f and also derivative of this value, which is we'll got here this one negative 0.090 and this one 5.8684, and then we compute x I plus 1, that is I is 2, we compute x3 here. You will got the answer 0.1450 with its error here 1.05%. So class, you can see here, for the first iteration, the error is 178.18%, and it's actually converged faster. Okay, converged fast compared to bracketing method, as the error decreased just up to third iteration. It decreased up to till 1.05%. So our conclusion here, after 3 iterations, the approximated root here x3 equal to 0.1450 with epsilon a equal to 1.05%. So class, this is how can you compute or you solve this problem by using table. Thus, we have completed how to solve the problem using Newton-Raphson method. But Newton-Raphson method subject to the following pitfall. This pitfall means that the advantage of the Newton-Raphson method. The case 1 here, Newton-Raphson method has the tendency of the result obtained from this method to oscillate around the local maximum or minimum without converge to the actual root. So here, for example, if we choose this one P naught as our initial guess, from here we draw a tangent line, we got this one as tangent line. And then from here we draw tangent line, we got this one is our root, and then we draw a tangent line again, this one as our root, we draw here, it will go back to this, initial guess. That is, it will not converge to the actual root. So it will oscillate around here, means that this is some of the problem about Newton-Raphson method. And then also, if you got the solution of the derivative of this function, that is your f prime x equal to 0, it will involve division by 0. If involve division by 0, you cannot proceed with the Newton-Raphson method. And then class, in some cases, the function also may be oscillate and has a number of roots. But the guesses that we choose here, it may jump and converge to some other roots, not the roots that we required or not the desired root. And then class, how to solve that one? We need to go to the second method. In second method, the derivative of the function sometimes, in Newton-Raphson method, the derivative of the function sometimes is very difficult to find or it is not differentiable. The alternative approach here, we use backward finite divided difference. That is, this derivative, we change it to fx minus fxi minus 1 minus fxi divided by xi minus 1 minus xi. And then from here, means that the second method, you will change the formula to this formula, xi plus 1 equal to xi, and the part of the derivative we need to change, then we rearrange, we got this formula. Class, you don't have to remember all this formula. The formula will be given to you. Okay? So the algorithm of the next method, which is second method, it will have the same algorithm as Newton-Raphson method. But the difference here is how can we compute the xi plus 1. Xi plus 1, we need to use second method formula instead of Newton-Raphson. Means that here you don't have to differentiate function. Class, for this example, we determine one real roots of fx equal to this function by using secant method with initial guesses. If you see here, you need two initial guesses, x, -1, and also x naught. Why? Because based on this formula, we have xi plus 1 equal to this formula when I equal to 0. Okay, let's say here I equal to 0. We will have here x1 equal to x naught minus function of x naught, and then x 0 minus 1, so x -1 minus x naught divided by function of x -1 minus function of x naught. Means that based on this, to compute this x1, we need information of x naught, and we also need here x -1, and also we need to compute its function. That's why, because of that, in your first iteration, you need two initial values. Okay, we need two initial values, which are here x -1 and x naught. So class, here, the question already gives us initial guesses of x -1 equal to 1.0 and x naught equal to 1.3. And then the question asks us to perform the computation until epsilon e greater than less than 5%. In the first iteration, we have here x -1 given in the question 1 and x naught equal to 1.3. So class, your first step here, you need to compute fx -1, that is f 1.0. And then you need to compute f x naught, which is function of 1.3. That is, we did it here. And how to compute this? Same. You need to substitute 1 in this x, okay? And then you use your calculator, you will got -17.4. And then when you compute for 1.3, its function, so this 1.3, we substitute in this equation, we'll have here -14.528. And then the second step here, we compute our next estimate, which is x1 equal to, okay, this is based on the secant method formula. X naught we have in the equation 1.3, function of x naught. Okay, this is function of x naught, function of 1.3, that is -14.1528, and then x -1 minus x naught, So 1 minus 1.3, and then we need to divide by negative 17.4. This comes from function of x negative 1, that is function 1.0, this value, plus function of 1.3, this value. Actually, it is minus here, but minus negative is become plus. So when you solve it, you got 2.6075. In this case, class, we need to compute epsilon A because we need to compare with epsilon as 5%. So how to compute this? We have actually in the question x negative 1 and x naught 1.3, and then we compute x1. Means that here x1 is our current solution, present solution, and this x naught is previous solution. So your epsilon A here equal to the absolute value of the present solution 2.6075 minus previous solution here is 1.3 divided by 2.6075 times 100%. So we'll got this epsilon A, which is 50.14%. If we compare with this 5%, okay, this 5% is epsilon S. It is greater than epsilon S. So you cannot stop your iteration. You need to increase your iteration. So class, same. You can use table in this case. In this table, we'll have here number of iteration, our I, xi minus 1. This is additional part compared with Newton-Raphson method. And then we have here xi. It's function of xi minus 1, function of xi. Then you compute your xi plus 1. This one using secant method formula. Then we compute epsilon A. You can try by yourself to do for second and third iteration. Okay, because here for iteration number 1, I0, this is from the question 1 and 1.3. This is what we did previously. Okay, and then we go to the second iteration, our I now become 1. So now xi minus 1 become x, here x0. This one become x I, so I1, so x1. This is function of 1.3, so you don't have to compute because already have here. Just write this one. And then function of 2.6075, you need to compute this one. And then you compute here x2 using secant method formula. Why here 2? Because I here 1, so here is for x. Okay, 1 plus 1, so x2. Then we compute epsilon A, which is this as current solution minus this one as previous solution divided by current solution times 100%. You will get here 31.72% error, still greater than 5%. We cannot stop. Then you need to continue to the third iteration. We did the same thing. And then for this one, we compute error 3.44%, which is now it is less than 5%. So we can stop at third iteration. Therefore, after 3 iterations, the approximated root of our fx is 2.0500 with this epsilon A 3.44%. This is how can we compute or we solve our problem using secant method. So class, as the conclusion, to compare the bracketing method and open method, for the bracketing method, we need 2 initial guesses, but open method can involve 1 or more initial guesses. For 1 initial guess, it is for Newton-Raphson method. And more initial guesses, for example, secant method, we have 2 initial guesses. And for bracketing, if you see for bisection and false position, the root is located within an interval. You have here XL and also you have XU. But for open method, not necessarily bracket the root because of this, we call it as open method. Bracketing method will always work but converge slowly. But for open method, sometimes it will not work. Okay, it can be diverged. When they converge, it will converge much more quickly compared to bracketing method. So class, it comes to the end of chapter 2. You will see more interesting topics in Chapter 3 on how we can use metric to solve a system of linear equation. Thank you for attention and see you in the next video.